Hello? Hello? Okay. So, do you hear me, my friends? Just a single yes from anybody. It would work for me. Can you hear me, my friends? Okay, great. So, after a long time, hello, everybody. Since it's been 1 month almost, I want to start with the review of the magnetostatics. In fact, we discussed magnetostatics only during the online courses. In fact, we have, I think, 3 more sessions left before our final exam, and I want to give some few details about what will happen in the forthcoming weeks. In fact, we don't have much left in topics to discuss. After this day, I'm planning to talk a little bit about Maxwell's other equations, as well as some introduction to the magnetic circuitry. And I think it will take 1 day also, and in the other 2 days I'm planning to make only all years, all semesters review, and to receive your questions. And in our meetings I'm planning to answer all your questions, and finally we will have a final exam. And okay, I can post it as a PDF as well. And the final exam, it's not clear in my mind the method, because still, just let me print it as PDF, because some of your friends ask it as in PDF form. Well, but there are 2 choices on the table: written-based or Socrative-based exams. But most probably it will be Socrative-based. But so many, how do you say, before, just a moment, Dropbox, oh here. Voilà, ordinateur. Here it is in the PDF form as well. So most probably, as I said, your final exam will be Socrative based, multiple selection, and as we did in the quiz. So that's it. And when the things become much clearer, I will inform you naturally. So let's start today's discussion. In fact, we started the semester with defining the magnetic field and the proper calculation methods. In fact, we defined several methods, several approaches in order to obtain the magnetic flux density, because it was the first term dedicated for magnetostatic we learned so far, and which is symbolized as B and the unit Tesla. There are different approaches. During courses, I mentioned this one. Each method has their own advantages in order to find out the fields. So we started by using the Biot-Savart's law, which was quite similar to the Coulomb's law, what we learned in the electrostatics. In fact, we said that the magnetostatics concept is based on the movements of the particles which are carrying charges. So in here, this the yellow segment, conductive segment, carries I current, and the current which is as a function of the electrons' movements with certain velocity and a certain vectorial direction. And due to this movement of the electrons, we obtain magnetic field in the surrounding medium of the given conductive material. In fact, this is the phenomenon itself, how we define. But when we made some calculations, as you also know, the product of the this vector direction of the given conductive element, it depends on the unit vector towards the observation point, or what we call as the field point. What I am trying to say is that at certain points on, let's say, dl infinitesimal distance vectors on the yellow segment, every single dl as could be assumed as a individual source points. So there will be consecutively infinite number of the source points. So, and we selected on this representation here single one of the dls among the billions of dls, and AR, the unit vector towards the field point, matters for finding the flux density, the B vector. And of course, this is not like the electrical field, not the dot product, but the cross product. So the angle between the dl and the unit vector matters, which is mentioned here as theta. So and we will have finally a beautiful pattern of the magnetic flux density around here, and which could be obtained by using the superposition principle. Voila. And we defined also a new constant, a universal constant somehow, which is the permeability, the parameter which lets us to understand the ability of material of the medium to magnetize the to be magnetized, let's say. And it's quite small for the air or the vacuum, in fact. And when we are making design, we are always looking for greater permeability. We will investigate the how do you say permeability concept more in the forthcoming semesters, my friends. So after Biot-Savart's law, in fact, we also mentioned that the interrelation between the varying dl. Okay, I will do that. Do you want me to post it now, Morgan? I think let's do it now, because I think some of your friends had difficulty to download it from Talk. Voila. Just a moment. Okay, document, lecture, ajouter un document. Okay, review. Voila. It's done, Morgan. So, and we established the link between the current flow and the magnetic field by using the right hand. So it's quite easy to investigate the direction of the magnetic flux density by when we know the distance vector as well as the unit vector towards the observation point or the field point. Voila. So in fact, here we also defined magnetic field as a and the magnetization. In fact, I didn't talk much about the magnetization here because it's generally in the machinery design. You have to take into account the ferromagnetic materials, but in this semester I will not talk a lot about the M factor. So the link between the flux density and the magnetic field can be established in the air condition by just factorizing the field with the vacuum permeability. So, after we defined the Biot-Savart law, we defined another rule which is identical to the Gauss law, what we learned in the electrostatics. Just flashback into electrostatics. In fact, the Coulomb's law, how it was tricky to calculate the electrical field, and the Gauss law by sketching out the surrounding surface around the field point, it was quite easy. In here, in the magnetism, Ampere circuit law works as in the same principle. In this case, we do not have such a surface, but we have an Amperian loop, which is we should enclose the field source, or in our case, let's say if this representation is the top view for a current carrying conductive wire, in fact, this circle could be a representative Amperian loop, excuse me. So, and the interrelation could be established by given in this formulation, and this is I think we solved many questions for this Ampere circuit law. Voila, and in fact, in here we mentioned that we don't care the type of the geometry of the Amperian law. So in here, A, B, C, in fact, the C is not cross-sectioning the wire. In fact, it's outside somehow. But they are totally different than each other. But finally, the superposition, or the how do you say, the magnetic flux density will be calculated, be the same. So our conclusion was the Amperian loops geometry doesn't matter for us, but for simplicity, you have to define the best geometry. For instance, for wire, instead of using such a rectangular loop, it's better to have such a circular shape where you can obtain the parameters by using the cylindrical coordinates. Because I gave you an example when we were talking about the Ampere circuit law in the past few weeks. In fact, if you try to calculate the dl for this Amperian loop, the A field, A loop, it would be quite easy. It will be 2 pi s, the diameter of the selected loop. But in here, the calculation will be a little bit difficult. You have to mention edge by edge this rectangular loop. So it's not appropriate to select B type of, how do you say, Amperian loop geometry. And C seems a little bit more complex because the diameter from the field point is not uniform, it's varying. What I am trying to say is you should be wise enough to select the most appropriate Amperian loop geometry. By the way, my birds, I forgot their door open and they are out before the lecture. I couldn't catch them. I hope they are not disturbing you because they are really excited. Sorry about that if it's disturbing for you. Anyway, so, voila, this is a short review, I mean the comparison between electrical and the magnetic field. And after the flux density in a real representation, we mentioned the magnetic flux, the identical to electrical flux. So if we flash back again to electrical field and the electrical flux, so it depends on the cross-section surface. So in here, it's the same idea valid. So if we have two different surfaces on our magnetic flux density plot here given, so the amount of the flux passing through the surface 1, the red one, and the surface 2 will be not equal to each other, even if they are same amount of the how do you say, same amount of the surface. This is because the unit direction, vector direction of the surface matters. What we are talking, in fact, the normal vector. In fact, let's focus on the surface 1, my friends. Here you see the 3D orientation of the surface should be normal to the surface. Well, we call it as AN or N. Okay, thank you, Elliot. So, and in fact, we mentioned that the product of the, how do you say, the in the magnetic field or magnetostatic calculations, we use the cross product. So some of the magnetic flux density passing from the surface 1 will be parallel, some of them will be orthogonal. So the superposition of all the flux density vectors cross product with this normal vector will be something different than the total amount of the product observed in the surface 2. So in here, the interaction between the ds vector and the flux density vector, it's really important. Well, in fact, we already solved some questions, and we will solve more in order to improve our understanding. So, and this is the interrelation somehow. Of course, if we are talking about superposition, the integral comes into account, so, naturally. So, and the unit of the magnetic flux is the Weber. So, in here, the first term, Weber per meter square, is Tesla. And voila, so the remaining, when we, the surface is meter square, voila, how it becomes Weber. So, in fact, we mentioned the magnetic flux in order to relate it to how the electrical energy is induced due to the magnetic field. So we somehow we mentioned Faraday's law for the first time during our discussion of the magnetic flux. Voila. So this is already we already discussed something, but in here also we discussed the BH relation, the Ampere circuit law, and the closed loop, the Amperian loop. There are several currents inside the Amperian loop, and the total field in the medium around such a system will be the superposition of the current. Somehow you should pay attention. I3 is in the opposite direction when we compared it to I1 and I2. So, and finally, when we brought together all the terms and wrote the H and the B relation by ignoring the magnetization, the M vector I mentioned before. So we obtained something like this. So what we mean here, the similarity between the electrical circuits and the magnetic circuits. Somehow, the right-hand side circuit is a simple electrical circuit where there is a electrical energy source, which is the electromotive force, and there is a resistor, and when you turn on the system, there will be the current flow, exactly as the same analogy. There will be something physically not how do you say physically not existing but theoretically existing, the reluctance, and the F is identical to the electromotive force, which is the magnetomotive force what we mentioned. So, and finally, the flowing energy, or the energy transferred from the source to the energy dissipating component, which is the reluctance, is identical to current, which is the flux itself. In fact, when we have a look at this last term, what we see here, the theoretical, the parametric expression of the reluctance, which depends on the length and the cross-section area of the design. So here, this formulation is obtained for such a toroid system. Somehow, the number of the turns around the toroid and the loop, Amperian loop, what we have here as L, matters, which is as a function of the diameter of the given toroid system. So, and somehow I also gave you this thing, but I don't want to talk because I repeat the same things. In fact, this was the first magnetic circuit I showed you. In the next year, we will discuss a lot these magnetic circuits by starting the second half of the fall semester, when we start discussion of the transformers, which is a very useful component in the electrical energy distribution. So when we have a look the simplest magnetic circuit, what we see here, which we let me go back, this one, this circuit I'm talking about, keep in mind. In fact, this is the physical version of that circuit. Somehow we have here the magnetic energy source, which is obtained by using the electrical energy. This current will induce magnetic energy, and the magnetic energy will be transferred to the reluctance defined in the system. So, in this circuit, we do not have a single reluctance since what we said, even air is possible to magnetize, but it's very, very difficult. You will need quite a lot amount of energy, both electrical and magnetic energy, to magnetize the air, because the permeability of air is very, very small. There will be two reluctances defined in this magnetic system. So here, the first term in the parenthesis is representing the core's reluctance, and the second one represents the air gap's reluctance. Now, I want you to think about the permeability when it's in the denominator, and you will obtain how great will be the reluctance value as compared to the core's reluctance. So this is what we are talking about. So, and in fact, what we can conclude, once the air gap is greater, the reluctance will be the greater, and the requirement for the and electrical energy to run the system will be greater as well. So, my dear friends, and after, if you do not have questions till here, I will continue by making us to remember the Lorentz law. I think everything is clear so far. So, and after these things, we started to discuss the other dimensions of the movement. In fact, when there is the movement, of course, we are able to talk about the force. So, what we are talking about, if in a medium the particle enters with a certain velocity, a single charge we are talking about, there will be a force appearing. So, and it will be perpendicular or normal, in other words, to the magnetic field in the system, the resulting force, and the interrelation between the force, the velocity of the charge, and the charge carrying particle, let's say, and the magnetic field could be established again by using the right hand rule. So here the term represents the angle between the velocity vector and the field vector. So in here, please do not make this v vector you confuse with voltage. So since we have E defined, when I define the when I ask, or let me say, voltage, I will use exclusively for this lecture E for voltage, small e, coming from the epsilon, and the V will be dedicated to the velocity of the charges or any field source. And we discussed a lot this, excuse me, we discussed a lot this figure. Here we have a certain uniform magnetic field, well, it's towards us, and in the white region where there is no magnetic field, in fact, when it enters to the system, you can justify it by using this right-hand rule I recently mentioned. So the force will be depending on the signature of the charge. Either if it's electron, let's say, it will be in the opposite direction, I mean in upwards direction, let's say, and if it's a proton, it will be in the opposite direction, and if it's a neutron, if it doesn't have any charge, of course the result will be zero. So in fact, in here, the most important thing when we discuss the cyclotron example, that the trajectory of the particle will be centripetal, or in other words, or the best term. So it will be rotating. So it will be circulating, let's say. So if we consider the quantum in the quantum domain, well, when we have proton in the center, which is merged with the neutrons, in fact, it will create certain amount of magnetic field in its neighborhood, and the electrons will tend to rotate with the speed of light, very high amount of velocity around the proton. This is in fact another justification of the Lorentz force. So what is important is that the amplitude of force is not affected from the how do you say, the magnetic flux density. In other words, let's go back to this analytical expression. Since it will depend on only the uh, amount of the charge, amount of the velocity, as well as the uh, B field, so, or the flux density. So yes, well, why it is equivalent to say magnetic force does not work. This is the reason, in fact, Gaeta, this is the point I am trying to express. In fact, excuse me, the magnetic force will only depend on the absolute value of the total charge and the velocity and the magnetic flux density. So let's go back to again this quantum example where we will have a certain amount of B field due to proton in the medium. So it will be uniform. It will not be changing by time, and the velocity will be constant around the proton, and the electron's charge, if there is no other effect around, if it's isolated totally, it will not change by time as well. So the force will not change, I mean the amplitude will not change, and since at t1 time the force will be F1, let's say, in T2 time, if the force is F2, the difference is going to be zero. So this is why the magnetic force does not give any work. Voila. Um, is it clear, monsieur? Voila, 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 voila. But what is important, as I repeat once again, the vector direction of force, the magnetic force, of course, will be changing. Or simply by using the cylindrical coordinates, it will be in, for such a system, I mean the quantum example of what we said, it will be phi direction forever. And of course, this was the case when there was only magnetic field in the medium. In fact, if there is electrical field also in the environment, the total force will be the superposition of the electrical force as well as the magnetic force. In fact, the first term here, the product of the Q and the electrical field, what we obtained during the electrostatics discussion, and so total force will be the superposition of both phenomena. In fact, and we mentioned the cyclotron example here in the two halves of the magnetic field area. There was a certain amount of electrical field which used as an accelerator, since in the upper portion and the down portion of the given cyclotron example, in these areas, we could not talk about the acceleration of the particles, which was possible only to obtain acceleration in the electrical field regions. But thanks to the magnetism, in fact, we could change the unit vector direction, which would let us very high velocity of the particles to be used in the cyclotron experiments. And voila, this was a very interesting exercise. In fact, the identical version of the forces in the magnetic field for macroscopic materials was called as Laplace forces. In fact, it was a specific version of Lorentz forces, since conductive materials are composed of billions of trillions of particles, charge carrying particles. In fact, the superposition of all of them would be the expression of the magnetic force for macroscopic systems, which we always, as electrical engineers, deal with. So here we have the current flow, excuse me, which is giving us an understanding about the direction of the electrons, and and the infinitesimal distance vector is the dl, or the infinitesimal length vector, or in other words, and voila, the magnetic field. So in fact, again, we may get how do you say, we may set the relation between the current direction and the field direction and the coming out force, the magnetic force, by using the right hand rule once again. In fact, you don't have to predefine any of your fingers. I mean, the first three fingers from thumb. You can define any of your fingers as a magnetic field and one another as current. And finally, you can the other third one will be the direction of force. But you have to be careful about applying properly. For instance, here, the direction in the upper rail here, the red one is the current direction. Apparently, the magnetic field is in upward, so the force will be from towards, I mean, transfers to the screen. Voila. And here is a good representation also how it applied the right hand rule. You can do it with your right hand and simultaneously. And in fact, superposition comes into account once again here. So the total force between each conductive lines, if there is no external field source, in fact, each one of these conductive materials will create certain field. What we mean, the I1 will create B1, and B1 will be affecting the second conductor. And at the same time, it's not mentioned here, the second conductor will have B2, which is affecting on the first conductor. So this seems quite like the Coulomb's law, in fact, the links between first charge and the second charge. But of course, we are talking about macroscopic materials, and Ampere's force law somehow lets us to understand the force relation between two or of course not two, more than two conductors analytically, the relation between each other. And you should pay attention if they are in the equilibrium, the forthcoming, the resulting F12, which is the force due to the first conductor, will be equal to the force the first conductor is experiencing due to the second one. So it will be in equilibrium equal to each other. So this formulation could be useful when you do not know the direction of the current. For instance, in an industrial application, you can use this analytic form. For instance, a matter, X matter, let's say. Imagine if there is behind a wall current carrying distribution line. By using your matter with a certain amount known current flow with a certain direction, you can find out the direction of the current flow behind the walls. So by using this analytical formulation. So, do we have any question so far, my dear friends? Apparently not. But in here, what is tricky? So we don't know the formula by heart. In fact, by heart, I will tell you at the end of this session, Esteban, which one you should know very well. But for specifically here, you should know this formulation by heart because it is a beautiful summary of electrostatics and the magnetostatics. In fact, the ones, if you know microscopic effects, you can find out for the macroscopic objects, macroscopic systems. So by heart, definitely for Lorentz and the Laplace forces, you should know this one. Voila. And because you can obtain the others by using your understanding and some right-hand rule. Voila. But for overall course, I will I will give you which are really important, and voila. So okay, and since in analytical approach, the cross product is in the account, the calculations somehow becomes a little bit tricky. In fact, in order to simplify the calculations, in our calculation, in the force calculations for macroscopic systems, a new term as called as force per unit length is used, because you should pay attention here in the upper formulation, my friends. There is dl1 vector and dl2 vector, and it's not constant in terms of vectorial evaluation. Well, since they are varying by time, once if we calculate the force per length, it will be really easy. In fact, in here, these crosses are not cross products at all. For force per unit calculations, they are regular product, regular multiplication. Voila. So, we called this exercise. In fact, I don't know if you did, but just apply your right-hand rule and try to justify these two things. Even at home, you will have enough time. Just with a Duracell battery or another one, you can justify this simple example, a simple experiment, excuse me, yourself as well. And finally, after force expression, force definition, one of the major parameter was defined, which is the magnetic torque, which is the ability of the magnetic force to change the type of the in fact, this is a very overall explanation, but you know, which lets the motion appear, my dear friends. So in fact, we defined such a system. We started with such a rotational system. The Brown conductor is not a straight line anymore. It is bent like a coil, and the vector definition of the current flow will be changing throughout the time. So I want you pay attention here that the vector quantity of current will change by time. What it means, my dear friends? It means that in here it will have a certain, even if the amplitude doesn't change by time, it will be, let's say, x direction, it will be y direction, it will be minus x direction, vice versa. So for straight line, in the upper example, we defined that the current flow by the right hand rule will be, I mean, for such a current flow, for a straight line will be in the phi direction. So keep in mind that in here, for this portion of the brown coil, here it will be circulating around, but in the when the current flow passes to here, it will change automatically. It will become no, orthogonal in this portion, and it will be in the opposite direction here. And here it will be orthogonal in the opposite direction observed here. So what I am trying to say, my dear friends, in fact, this beautiful design will change the dynamics of the force dynamics, let me say, overall. And of course, it will change the work, the cumulative work due to this system. And it will be depending on the spatial relation between the magnetic field and the electrical current. So what I am trying to say here, if we have a uniform B field, which is labeled with the dark blue arrows here, in fact, its direction will evolve. I mean, the theta angle, what I am trying to mention, my dear friends, the spatial changement, it will play an important role on the cumulative torque, cumulative magnetic force. What I am trying to express as a conclusion, my dear friends, in such a system, if we are talking about the force phenomenon, we have to consider that it will be time-space dependent. So I repeat again, in such kind of systems, the resulting force will be time-space function. Well, we will discover each portion, I mean the time dependence and the space dependence, by time together, my dear friends. And here, simply, when we first defined, if if they are parallel to each other, there will be no force. It will, the angle between each other will be 90 degrees, and voila, it will be 0. And here there could be possible to talk about the rotation when they are parallel to each other. So in fact, in here we formulated these concepts by using this simple formulation: the torque, which is symbolized by tau, small tau, and the r vector, the distance of the charge carrying element to the rotation axis, or pivot, what we say in a terminological way. And it will depend on, of course, the vector of the magnetic force. And here, how the space I mean spatial variable affects the resulting torque, you may see the reason here, the sign of 0 and 90 by comparing the maximums and the minimums. Voila. So for a simple coil, a rectangular coil with a single turn, the total torque is obtained as a function of the physical dimensions as well as the uniform flux density in the system. And one may pay attention that W times L, the width times length, gives the area, the cross-section area of the given geometry, rectangular geometry. Voila, for n number of turns which is possible to talk for the machineries, in fact, we will define this is the rotor, the rotating part of any motor. It will generally not be composed of single turn, multiple turns we will talk about, of course. And finally, the torque will be depending on the cross-section area of the rotor and the number of the total turns. Voila. So we will revisit once again, and we mentioned different sketchings here. What we saw that when the angle between the field and the current flow is 90 degrees, and it's gonna be the maximum, and when it's parallel to each other, the resulting torque will be zero. Anyway, I will skip this one. If the things are clear for the magnetic torque, I will continue to the Faraday's experiment because we had some difficulty, especially the Maxwell-Faraday's law. So this is important part. I want to spend more time on this section. Any questions so far, my dear friends? Are you still there, by the way? Okay, we have plenty of participants. That's good. So. Good, my dear friends. Voila. In fact, as you pay attention, my dear friends, step by step, we came to a certain point where we have all the ingredients now. By using Faraday's law or by applying the recipe of Faraday, we will have a beautiful, phenomenon, the changement of the type of the energy from one form to another form. What I am trying to say, in fact, by using what we defined so far, it will be possible for us to change mechanical energy to magnetic energy, and then magnetic energy to electrical energy. Yes, you are right. I'm talking about the principle of the nuclear energy plants, not solar energy. It's electrochemical or hydro energy centrals, etc. So it's really depending totally what we mentioned, my dear friends. Here, one day again, Faraday tries this simple example. He has such a toroid which composes of two electrically isolated coils, and with the isolated second coil, he connects it to a meter. I mean, electric ampere meter or voltmeter. We don't care. And once he switched on, lets the current flow here, he observes, in fact, in the beginning, a certain ripple. This is the beginning of the Faraday's law. But after he keeps running the electrical energy, energizing the first coil forever, that he sees the matter doesn't move. In fact, we have to understand this portion very well. Because of the current is steady, let's say DC current, the T1, T0, IT0, IT1, what we mentioned here, are equal to each other. What happens? In fact, for the I0 case, the current flow here in our previous lecture, we pinpointed them as these red arrows. Due to these red arrows, by using the right-hand rule, we will have such magnetic flux density around the coil. And there will be certain flux which is interfering the secondary coil. So, which means that they are electrically isolated but not magnetically isolated. So, and in fact, we already found a relation by using the Biot-Savart's law that the distance between the field and the field point and the source point is important, and then we will obtain that certain amount of B is going to be affecting the second coil any time moment. And finally, in I1 to IT1, there will be the same amount of magnetic field affecting to the secondary coil. So the difference will be zero. So there will be no changement at all. So as in fact, there will be defined magnetic energy here, but there will be no electrical energy. This is the point. In fact, what is very important and beautiful is that this formulation defined by Biot-Savart, the reversibility of the electromagnetic formulations or electromagnetic phenomena. So, which means that here electrical energy creates magnetic energy, here magnetic energy is abundant and it creates electrical energy. But since the steadiness of the magnetic energy here is the case due to the steadiness of the electrical energy in the first coil, there will be no electrical energy induced. This is very important part about the Faraday's experiment, because in the next part, excuse me, he makes such a switching, with a certain frequency. He ons and offs the switch, and finally it will create intermittent pattern of magnetic flux density. And because of the inequivalence of the reflected magnetic flux density to the secondary coil, there will be a differential form of electrical energy observed in the secondary coil. Somehow, some portion of the energy source here will be transferred to the second coil. So this is the Faraday's experiments story, my dear friends. And of course, thanks to the thermodynamics, what we know, the total energy in the medium will be preserved, of course. So because we will use it a lot in the future for machinery design. I repeat once again, the cumulative energy defined in the system will be preserved, since some of the source current is transferred to the secondary portion of the system. So, of course, Faraday taught more than what we are discussing now, I'm sure, and after he decided to formalize this one by using the relation between exactly, this is electrical transformers basics, Maha. Exactly. In fact, this is the principle. By knowing some features of the electrical dimensions and the magnetic dimensions, we will make specific designs. For instance, people make this already for your computer charger or your phone charger. In fact, they are transforming by using this very principle, my dear friends, making it appropriate, utilizable by your phone, the network energy, which is 220 volts for Europe, with 50 hertz. And by using this principle, we supply 5 volts energy, electrical energy, to our telephone. Voila. And I repeat, this is exactly based on this law. So, and finally, I want you to keep in mind this expression, the differential form of the magnetic flux as a function of the T, because here the timing of the switching here matters, what Faraday showed us. So by this magnetic flux density, there will be a certain amount of flux flowing in this portion of this system, overall system. And what we know, the flux is as a function of the cross-section area of the design. So since the cross-section area will not change, it will be depending on only the flux density. So by time it's the partially derivated form of the magnetic flux, somehow the induced electrical energy in the secondary coil. Well, but something was missing with the Faraday's definition. This is when Monsieur Lentz made such a proposal as putting only this minus signature in the counter effect. So, in fact, here, if we look at a single coil, my dear friends, so far there will be a certain B field, and naturally the magnetic field will be showing such an effect of buffering any change in the overall system. What I mean, in fact, if we go back to here again, there will be B field due to the first coil, 1 point. And in the second coil, for this one, at any very, very infinitesimally small time moment, there will be a certain amount of current flow here in the coils. Let's say this is one of my coil. And this coil, this current flow, I want you to obtain, use your, how do you say, thumb and the right hand, my dear friends. If you apply for the induced one, what I am talking about, induced means due to the first coil, there will be this red coil inducing the electrical energy in the secondary coil. And in fact, due to this current flow, there will be a certain amount of B defined to the system to counter, to balance the magnetic field in the system. So balancing means, in fact, it's making it to trying to make it zero. So which will be in the opposite direction vectorially. So this is how the length came, how the length contribution to the Faraday's law came into account. In fact, it seems a bit abstract. I will come back here again after I show you this experiment. I already showed you, of course. In fact, here, what we are talking about, the Faraday's experiment now is done by using only a magnet. There is no electrical source. Again, the same matter. Here, when the magnet is stationary, of course, it's possible to talk about the magnetic field around. There will be. But since it's steady, there will be no differential, how do you say, the differential flux will be zero. So consecutively, the induced electrical energy will be zero. And here, when we move it with a certain velocity, in fact, the 3D position of the magnet will be changing, so the distance between the source and the field will source and the field points will change as well, and correspondingly there will be a differential current somehow. And of course, the velocity will matter. And once if we change the direction, there will be the opposite direction. In fact, this is this experiment could be used in order to understand this link between induced magnetic field and the secondary magnetic field induced due to the induced electrical current. I repeat once again, I feel you may be confused, my dear friends. The story starts with the B. The B is due to the first coil here. So, primary magnetic field, which creates the electrical energy in the secondary one. And due to this one, there will be this one. Everything is okay here. And in fact, the system will tend to compensate it with a counter magnetic flux. And so this is also possible to see here the opposite directions of the magnetic field. So this is how we obtain when we merge these two approaches. In fact, as you notice, Faraday looked the system, this electromagnetic system, from electrical perspective, and Lenz looked it from somehow the magnetic perspective. And once you merge these two, this minus signature finds its meaning. So for a single turn coil, single turn geometry, the induced electromotive force will be as a function of the partial derivation of the flux in the system with respect to the time. Voila. And for a multi-number turns of system, it will be factorized by the number of the turns. My dear friends, as I said in the beginning of Faraday's law, I said this is the very pure principle of or mechano-electromagnetic energy conversion. In order to understand those kind of hybrid systems, we have to understand well Faraday's law, my dear friends. So, may I continue? Do you need break? May I continue? Or do you have any questions? In fact, if we continue, we may finish a little bit early. Okay, great. So I continue. No need to respond for Paul. Ignore it, my dear friends. So Faraday's law. In fact, this is just a matter of understanding the interrelation between all these vectors. In fact, in here, what we know, the flux density is as a function of the cross-section area, what we said, and the magnetic flux density defined in the medium. So there, since it's the dot product, and the angle between the normal vector of the cross-section surface and the magnetic field matters. So somehow, if you, for instance, in the moving systems, when this system becomes, let's say, movable, in here there is very tiny changement of the how do you say the normal vector of the cross-section area. But imagine if it was different, if it was moving, what I try to say, it would be changing as well, all the parameters. So in such kind of constant system like electrical transformer, my dear friends, it will be constant. So when you plug your charger, for instance, this is why you don't worry about the direction, I mean the changement, because it's constant. I mean the spatial distance between each other, etc. But in here, this example is dedicated exclusively for rotating systems, my dear friends. But it's not very difficult because it will be somehow plotting something between 0 and 1, thanks to the how do you say, cosine 0 and cosine 90. Voila. In fact, I want you to think that if then we move slowly with certain velocity, of course, from 0 to 90 degree, this charge carrying element, then what would be obtained? Can you tell me what could be the pattern of this flux? I repeat again the question. Imagine if you have a uniform magnetic field, my dear friends, and this element is rotating with certain velocity between 0 to 90 degrees. So I am asking you mathematical pattern of the flux function. How would it be? The answer is very simple. The cosine alpha in here varies between 0 to 1, minimum to maximum. And here it will be changing between these two values, and the flux function should seem like a very famous function you know already. And you will say hallelujah, in fact, when I say the answer, if you can't answer. Any answer? Okay, let's make things a bit. I will give some extra points if you give me an answer. I repeat the question. What happens in the existence of uniform magnetic field? I rotate such a conductor with certain velocity between 0 to 90 degrees. I am asking the pattern of the flux function. Okay, no answer. In fact, the pattern will be a sinusoidal function, my dear friends. So now I think you can see the big picture, huh? Why the network electrical energy is sinusoidal, the AC circuits, what you learned this semester, and it has 50 hertz or 60 hertz in United States. In fact, this is the very core principle, my dear friends. In fact, during the electrical energy generation, the spatial position is varying by time, and this variation changes the total flux exposed, which will carry the magnetic energy to the system. So this will change, as I said, between 0, the minimum. Think about the sinusoidal function, and with the peak point or the maximum, when the angle between the field and the geometry is 90 degree, the normal vector of the surface is 90 degree, it will be the maximum. And then with the decreasing in the opposite direction, it will be the decreasing portion of the sinusoidal function. Voila. Exactly. N vector, Quentin. When we talk about the n vector, I think I expressed it here. Okay. Where is it? Okay. Oh my God. So n vector here I defined it. So Kantan, look at here. So in this this is a simulation of a single charge carrying conductor. We are looking from the top view, and there will be specially changing vector flux density all around. In fact, here this blue arrow on the red surface is the normal vector. This is the n what you are mentioning, and it will be always orthogonal to the surface you selected. But in our system, what I recently showed you, my dear friends, well, it's here, this one. So with your hand, please try to use your hand. Imagine from your the red arrow is the n vector. It will be rotating, in fact, by time. So, okay, vector. You like to play games. So, I repeat once again, this is gonna give the pattern of the flux as a sinusoidal function. Voila. So, and of course, we see it everyday life in everywhere. Voila, voila. So, any questions so far, my dear friends? Voila, I can receive some questions. Well, okay. Let's make a single. Okay, good. So imagine, Kantan, I want you to think for the case, or maybe I can carry it directly, or directly this one, cosine theta. Voila. So when the n vector is just like this. Okay, maybe it's better if I use a representation. So this is important. Why I am taking my time. Let's say this to be the b vector, my dear friends. Oh my god, excuse me. So I want to make an animation, if I can manage very quickly. Voila. So let's say this to be the b field, which is okay. Oh my god. Voila. So, and in fact here, this is the cross-section area, which will have also, as we said, the normal vector. So, and let's say in this position, this is the normal vector. Okay, voila. So a different color to differentiate the normal vector. In fact, here the normal vector will be like this. In fact, the value of the normal vector will be total area multiplied by the unit vector. As I said several times, this is the unit vector, my dear friends. So I want to, sorry, Control C, voila. Excuse me, it's time taking, but we have to do it maybe in order to. So voila, in here, what do you see, Kantan? Can you tell me, please? Here, alpha is 0, right? For this case, 0 degrees. So I will have, for the first case, cosine 0, the maximum, voila, the maximum of the flux in this position. Let's move it a little bit, huh? Like this, tuck, 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 like this, and pay attention. The unit vector is like this, so I am rotating this one like this, and B is uniform. I want to make it something like this, 45 degrees, huh? Minus 45 degrees, let's say, and it will be BS over over square root 2, right? The cosine 2, something like that. It will be minus signature, but we don't care. Let me put. And after, when I continue with the external physical phenomenon to like this, again, unit vector is always orthogonal to the surface. This is the point I think you have difficulty to understand. So when it becomes 90 degrees, then it will become 0. So now I am going to paint. So what I am going to do is I will put simple, okay, I know it's taking time, but it's the best way to express, I imagine. Okay, voila. So let's say this is my timeline, okay? And at 0 point, I have maximum. So BS, voila, is here. Oh God. BS is here. And in here, there will be minus BS over 2. Voila. Copy. And here, okay. And here it will be 0 when the angle is 90 degree. As I said, it will depend, oh God damn. Okay, 90 degree. So side down, okay. And when you convert it, it will be exactly like this. Opposite, vertical. Okay, voila. Something like this, or maybe I can stay here. If you connect, I just made it for 3 points. If you connect all these points, it will be a quarter of a sinus signal, right? If you do it for different signals, it will be always like this. I said it's a sinusoidal. Now it makes sense, monsieur. So this is the flux function, flux as a function of time. This is important point, my dear friends. Okay, is it cool? It's great, right? You know how this sinusoid electrical energy is induced. So this is why we use in everyday life this kind of thing. So voila. Okay, if you do not have any questions, I want to continue. I keep it somewhere below here. Okay. So, okay, do we have another? Okay, I'm not sure to understand everything with the torque. If you can explain after that. Oh, yes, of course I can. With the torque. In fact, maybe it's time to talk how we merge, because after I will give you the Maxwell's contribution to Faraday's law, and then I will finish my lecture today. In fact, my dear friends, this is purely the observation of Faraday's and Lenz's to the same phenomenon. In here, as you see on Faraday's and the Lenz law, we do not consider the forces. But of course, there is a factor which lets this guy to rotate something like this. And this is the torque itself, or the magnetic force itself, Adrien. What I am trying to say in here, I don't care when I am investigating or when I am looking from the perspective of Lenz's Faraday. I don't care the evolution of the how do you say, distance change between the surface and the magnetic field, but I am just looking at the flux electrical energy relations. Of course, the phenomenon here which lets this blue disk or the material to rotate is torque itself. Now, by keeping in mind, let's go back to our torque example. Here, let's see. In fact, let's say something lets this coil to rotate. So we are looking from the top view, huh? And here there is a uniform magnetic field, and due to this one, ignore this I in, I out, huh? Just think the fluxes induced in here. So at this distance, there will be a certain amount of flux which is defined to the system. It will be parameter of the space function. So what I mean in here, we are not looking the problem, we are ignoring the time variance or time variability, in other words. In here, excuse me for the birds, by the way. In here, the theta matters, the angle between the distance between the rotation axis as well as the field point. So, and it could be the torque source, a water flow, or a steam power, or whatever. In fact, but this is defining a rotation in the system. Magnetic torque defines a rotation to the system. And this rotation causes the changement between the uniform magnetic field as well as the unit vector, which will change the pattern of the induced magnetic flux. And what will happen? It will change the pattern of the induced electrical energy. So I can feel you. It's step by step, but torque induces the movement, and the movement induces the changement of the flux or magnetism, and it induces the changement of the electrical energy. So sequentially, so this is how you can establish. But with the real life examples, of course, we will bring together. For instance, I think your first exercise this afternoon we will discover together. The first one, for instance, not torque dedicated. Maybe I can bring some kind of torque electrical energy exercise for this afternoon, and not this one. Anyway, okay. So I don't know if you could find your answer, Adrian, because you asked not sure to understand everything. I don't know which kind of things. All the torque, or you couldn't set the link between, or was my explanation clear? Just let me to understand, or you can detail your question in your mind, and the others, please ask which part. Okay, let's go back, go away from our lecture. In the physical dimension, the torque concept isn't clear. Is that correct? What I understand what you say. Okay. So, okay. Um, in fact, for the ones who have difficulty to understand torque, I will, let me see, I should have a textbook um, for you to read because it's important. Okay, this one, I think. There should be a chapter about torque. I will share the corresponding chapter for you, but the problem is, where is it? Work energy under here, torque, rotational motion, voila, here should be, yeah. Okay, it is very good. So, for you, Adrian, and for the other people between 245, 270, 200, 245, 270. No, 312. 312. Voilà. 245 cancel. Excuse me, 245. 312, 270, 312. Voilà. Anyway, I will send you this chapter for you to read immediately after the course. I don't want to lose time now, but I will give you a very beautiful textbooks chapter, and you may read it because before I told you in the previous I advised you a textbook of survey. I have the printed edition, but not the soft copy. But you can find it easily somewhere. This textbook as well as surveys textbook, but I follow surveys textbook, which is I am familiar. But this one is also very beautiful written. So you should read because it's a little bit out of scope of our course. I cannot get into details of the torque here. So please read it and bring back the magnetism and the merge in your mind, and voila. So then I continue, my dear friends. I will, in fact, this is how the principle of the generators are established, but we will not get into more details. Well, today I want to continue, the Stokes theorem. In fact, the, it's a mathematical tool. I gave you the fish farm example, but let me make a poll also. Please respond to this poll as well, my dear friends. Hello. Can you check the poll I published recently? Oh my God, I think talk has crashed. Anyway, okay, not really. Okay, not really. Okay, understood. I got the message. Okay, this is something else. First of all, I say again, Stokes theorem is a mathematical operation. Okay, I got the message. More than majority couldn't get the point. In fact, here we have we have different methods to make calculations of how do you say a surface or circumference. In fact, I told you in here, let me go back here before I start. When we have such a function f, and let's say it to represent the water flow, on a river, and where I have a fish farm, which has certain area. I think this is clear. In fact, there are two approaches for me to calculate the total water flow inside the fish farm. In fact, first method is calculating it by looking to the fish farm very microscopic way in order to obtain the flow or the in every single millimeter square or nanometer square of the fish farm. So which are the small fluctuations or small flows present everywhere in the area. So, in fact, in the earlier classes, what we said, in order to calculate the variation of the water flow in such kind of river, you have to apply the cross product. Or here, this is the del operator, my dear friends. We have to calculate the curl of the function in order to calculate these rotations or the movements of the water in every dimensions, x, y, z. Think about that. So, and this is the first method to calculate the total water flow, water flow changement in the system, in the fish farm. And finally, there will be billions of this kind of curls in the predefined area, and the superposition of this one, which will be, I mean, after I sum them up all those small pieces, and this will be the curl of the water flow function in the defined surface. So exactly. But let's isolate ourselves from the torque for the moment, because now purely since I am not a mathematician, I am trying to express it mathematically first. Let's not confuse with the torque. Of course, it seems like the torque. Yeah, it exists everywhere in the water. But what I am trying to do, in fact, I am trying to understand the regime of the water flow changement in X, Y, and the Z axes. So this is why I am applying the curl here in the first, I mean the all around the surface. So of course, the water flow from top to bottom of the river, imagine it will be changing, the unit direction and the unit vector on the amplitude as well, but also its relative dimension of the or relative orientation of the surface of the fish farm will be changing. So this is as a vector also, even it's not given, how do you say, the arrow above, and the product will give us a scalar, and it will give us a total amount of the water flow in the fish farm. So, and it will be the strength of the water flow for our fish farm example, not the direction or the vector information will not be possible for us to capture. For this purpose, you should only stay on the first part of the calculation, which is gonna give you at how do you say, at small fractions of the river or the fish farm, which will give you the tendency of the movement of the this surface relatively to the fish river water flow. Voila. And in another approach, there are so many arrows here, excuse me. In here, another approach to calculate the total water flow in here by just calculating the perimeter, and pay attention, it's not gonna be constant, it's varying in terms of vector direction, it will be varying. And to just calculate the divergence or with respect to the divergence of the water flow function with respect to the how do you say length vector. So finally, this product, which will be equal to the same thing somehow, both calculations are independent, my dear friends, pay attention. When I apply them to the same function, in one side I am using the divergence of the curl, and in the other part I am just using the divergence with respect to another function, another variable, let's say. Here, pay attention, it's by the surface, it's here the length vector. So if this is clear, because this will give the same thing what we will obtain here mathematically. And pay attention here, f is the same function, the water flow function. So mathematically, this is called as the Stokes theorem, my dear friends. In fact, it's quite analogs to the electromagnetic systems as well. If this is a little bit clear, I will continue to apply it to Faraday's law, how it's applicable. So let me make another poll. Please respond this one, my dear friends. Stokes. What is this? Arthur, what is this? Anyway, really, je comprends mais pas what does it mean. I'm sorry, I'm a little bit okay, not yet clear. Okay, I have to think about. Oh yes, I have another example for you. Okay, I want to give a very short example, and then I will tie the things up and then finish. Okay, we'll talk about this meme later. In fact, the guys who are not clear, I want you to think about a balloon, a hot air balloon, okay? And let's say this is the circumference of the hot balloon, and there is an airstream, uniform airstream in Lyon, for instance, and we are investigating the total force in the balloon, which lets it to elevate in the air. Voila. So the airflow function here is F, my dear friends. In order to, of course, from the thermodynamic perspective, the changement, pressure, air, and the temperature changement will depend on the interrelation between the outer medium and the inner medium. This is something else. I assume you already know about that. So, in order to calculate the cumulative force here, again, we can get profit the Stokes theorem. For instance, if you don't know the shape of the balloon, well, or if you do not know the surface, but you know the one cross-section perimeter of the given balloon, okay? So what you can do is, first of all, let's start from here. You know the floating phenomen's value with a barometer, for instance. You measure it and you apply the here divergence to with the perimeter of the balloon. So which will give you the total phenomenon you are concentrating on your about your balloon. Let's say the elevation force, okay. And in the other part, in order to calculate the same phenomenon inside the balloon, you have to know the affecting parameter everywhere inside the balloon. So it's exactly the same thing what we tried to say during the fish farm example. So you apply the changement, differential changement of the air inside the balloon in any every dimensions, and when you apply it all around in the all volume of the balloon, of course, you have to sum them up, all of them. In fact, here you have to apply again the the surface of the balloon you have, which is capsulating the total air inside, which lets the phenomenon appear. Voila. So this is the method in order to understand this affecting phenomenon. And finally, Stokes' theorem proves these two mathematical operations will give the same result. And okay, it's a change, not the changement. What do you mean, Thomas? Okay, let's continue. In fact, we have 9 minutes left, unfortunately. I want to keep going and okay, thank you so much. So, sometimes my English is not very well. Thanks for improving. So, in fact, we apply this one to Faraday's law in order to obtain the electrical field and the magnetic field relation. So what we obtained from the Faraday-Lenz law, that the link between flux and the electromotive force like this. And what we know also from electrostatics, that the line integral of the electrical field here is the voltage potential. So we brought that knowledge into our consideration here. And finally, we brought all the things together. And finally, we could express the line integral or the voltage potential as a function of the magnetic flux density. But here, what is very interesting is that you should derivate partially the magnetic flux density with respect to the time. So, in fact, this is because Faraday's law mentions again, remember the switching. In fact, this is the analytical expression of that switching act of Faraday. So, voila. In fact, when we brought together all these electrostatic and the magnetostatic knowledge, what we see here, there is one side line integral, one side surface integral. So, okay, it seems like exactly this one, huh? So, then I'm just copying it here. Seems quite like this. If you ignore, for instance, in here, Stokes' theorem proves that equivalence applies when f is the same vector, but this is gonna be another vector. So I realized something thanks to the Stokes theorem, between electrical field and the magnetic flux density. Thanks to this theorem, I repeat again, so one side here represents to this part and the other part represents to this part. So when we keep going, we find out that this beautiful expression. So the curl of electrical field gives us the magnetic flux density itself, or flux. So this is just how we use the Stokes theorem. Only I repeat once again, my dear friends, the Stokes theorem, because f is another function, but here let's say f is the electrical field function, you can see precisely, and the del cross electrical field equals to this one somehow. So here how we obtain the Maxwell-Faraday's law thanks to the Stokes theorem. I didn't do anything except just bringing my knowledges. In fact, another thing you should know by heart is all these formulations. Of course, Stokes theorem is something. How do you say? If you want to know, it's good by heart. Okay, how to use the del operator in this case? So in this case, for instance, for electrical field to have um, EX AX plus EY AY plus excuse me, oh no no, AZ AZ. Okay, so and this is how do you say, think about again the water flow, please, Kantan. And here your electrical field will have three pole combinations for Cartesian coordinate, what I say. And for Cartesian coordinates, del operator is to apply EX dx or E because it will not apply to Y and Z. And the curl you have to obtain, I don't know where I defined. Okay, spring okay. So simply it will be equal to, I don't want to rewrite because it's a very long. Oh yes, okay. Voilà. So it will be simply like this. So electrical field will be AX EX, and then for this function it will be, maybe I can create another file. So Control X, Control V, okay, it's here and it's here as well. So what we are willing to do is to apply, let's use this formulation instead because it will be more utilizable in our calculations. And dl vector, and this result first of all I want to write it down, maybe voila. Excuse me, it's taking time, but at least it could be as a good to cover all in a single piece. So in here So here you can isolate, if let's say if it has a x, then the divergence, of course, will apply only the x dimension displacement. And for the application, this is one method to apply directly the, how do you say, our conclusion when we bring together the things. And if you want to apply the Stokes theorem, so you can simply, I want to put it back here. So in order to find the electrical field and the magnetic field relation, I just rewrote the things, in fact, nothing original. So, but I brought the things all in a single presentation. So, if you want to isolate one of the unknowns when you know one thing, either you can use this method where I just picked up the things one by one from Faraday, from line integral of electrical field, and I merged them, and then I found this equation. And or you can just apply the Stokes theorem in order to, for instance, calculate B fields when you know electrical field, or vice versa. Voila. So VS, well, VS, well, Stokes theorem, let's say, let's keep it applied on electric field and magnetic flux density. Voila. So it's just a comparison. I share it with you, and you. Voila. So that's it. And if we have time, I would like to do this exercise, but we can end the lecture, and we can start with this exercise. But it's very simple. Okay, guys. Okay, thank you so much for your time. As I said, since we do not have much chapters to discuss, we will make a lot of review, and we will solve a lot of questions in the last three lectures as well. So please review the earlier exercises. Yes. Voila, when you are studying, please revisit the previous exercises and send me in advance, and I can prepare my presentations based on your based on the feedback from you, and voila, then we will have our possibility to improve our knowledge. Voila. So thank you so much for your time, and I will upload this presentation and the chapter about the torque to espace. I think it's better. And then see you in when is it? In 1.5 hours. Voila. So 1:30. Ciao, bon appétit.